So, we are going to be using this graphical representation of systems quite a bit. We've seen them a little bit before, but I wanted to kind of go into them in a little bit more detail. Or actually, I guess use them and set them up in this specifically feedback control way that we'll be doing a lot of. And yeah, so it's block diagrams and feedback control systems. So a useful tool for designing control systems is the block diagram. The plant and the controller are represented as blocks. Okay, so this will be the plant. And we often will say that the plant has transfer function G of S. So we'll, in the beginning of our control system work, so in this class, we'll mostly be at the very beginning of control system exploration, right? We'll almost always be using a transfer function to represent the plant in this class. So you can also represent it as a state space model, a frequency response function. There's all kinds of stuff. You know, all of the versions that we learn in system dynamics we can use, but we're going to focus on the transfer function in this class. The plant. And then we're going to also have a controller, C of S. So the controller has a transfer function as well, and we often call it C. Okay. So usually a transfer function or transfer function matrix can be described, can describe the function of each block. A typical block diagram is shown. In this configuration, a command function R, so we're going to label this R, and this is what we're going to call our command, is provided to the control system. This is what we want the output of the plant to be, okay? So say the output of the plant is an angular position, okay? And say we want to control it to be at 90 degrees, the output. We would then, if we want the output to be 90 degrees, we would make our command 90 degrees, okay? It's nice, instead of having to guess what you should put into the plant to make the output what you want, you just put in 90 degrees, and then your control system in this feedback loop is going to try to make that happen, okay? So you command 90 degrees. What you want to do is you want to compare what is the actual output right now. So the actual output we often will call Y, right? In keeping with our notation of Y being the output of a system. We're going to feed that output back. So we call this feedback. So we measure the output. We compare it to what we've commanded. So if we said 90 degrees and it's 80 degrees, it's off by 10 degrees, right? So we want that difference to be 0. Okay? If there is any difference there, it's an error. So we call it E, error. That's something we want to make 0. This is, of course, a summing junction, plus and then minus. The minus sign is denoting what we call negative feedback. Okay, which is to say, when you have an output, instead of summing it with the command, you're subtracting it from the command. So, negative feedback. What's left over is the error. Now, the error goes into the controller. The controller is going to decide what to do with that error. We're modeling the controller as being a transfer function. So it has to have an input-output behavior, right? And in fact, if you have a transfer function that is operating on 0 as the input to it. So if 0 is the error, what is the output? Do you guys know what that would be? To justify it in complete detail, it takes a little bit of a calculation, but it's essentially 0. So if you put in 0 to a transfer function, you're going to get 0 out. And if I could easily sort of justify it. We call this, I'll label this first and then I'll justify it. We call this the control effort U. So whatever the controller puts out, U, goes into the plant. And now we've completely closed this loop. So the output comes out, whatever it is, 80 degrees, comes back. Command is 90 degrees, we subtract. We get 10 degrees of error. Goes through the controller. Controller decides what to do with those 10 degrees of error, okay? Comes out as U, the control effort, and that's what we put into the plant. So this is going to be, for instance, like a voltage or something like that. So a voltage going to a motor that's going to change the angle of whatever this angular position is we're controlling. So maybe a robot arm or something. So this is our sort of complete feedback loop, and I'll justify for you for just a moment. If the error is 0, you know that from this block diagram situation that U of S has to be equal to every block in the block diagram can be read as being the transfer function in the block diagram multiplying in the Laplace domain, operating on the input, which is E of S, okay, the error in this case. So if the error is 0, then 0 times C is 0, so U of S is equal to 0. If you take the inverse Laplace transform of 0, what do you guys think it is? 0. Yeah. Okay. So that's cool. So in other words, when the error is 0, our control effort's 0. We don't need to do anything. When the error is non-zero, we're going to get something. The controller is going to do something, depending on how we've designed it. So most of what we're doing is designing what C of S is going to look like. We want to make C of S such that our output performance characteristics, so in terms of transient error, in terms of stability first, right? Transient performance and steady state performance is good. So say our command is 90 and our output's 90. Then we suddenly change our command to 0 or to 14 degrees or something. Immediately we'll have error, right? There will be error, and our controller is going to start operating on this plant. It's going to start, trying to make something happen, and then hopefully our output will go to 14 degrees, the new command, right? But it goes to 14 degrees, first of all, hopefully stably. So that's one performance characteristic. It also should go there in some, finite amount of time, maybe like within a certain time. Maybe we don't want it to overshoot. These are the transient performance characteristics. And then we also want to go perfectly, or at least as closely to 14 degrees as we can, as what the command is as we can get it to. So maybe 15 degrees is okay, but 20 degrees would be not okay, for instance. So this is like, this right here, this diagram is like our bread and butter. We always come back to this block diagram, okay? And this block diagram is really just a way of visualizing, a really useful way of visualizing an algebraic relationship among all of these Laplace domain variables, okay? And it's really common to use this. So control systems, like, it's all about the block diagrams. this is the way people represent stuff in control systems, is in block diagrams. So you got to get buy into these, but this is like the main one that we use. This is like the fundamental one. We build off this going forward. So we recognize that this is representative of these algebraic relationships. For instance, that the error is equal to the command minus the output y. That's an algebraic relationship. U is equal to C times E. That's an algebraic relationship. Y is equal to G times U. That's an algebraic relationship. So these algebraic relationships are encoded into this diagram, and it's a useful way of visualizing things. Okay. So the three algebraic relationships that we need to consider here are shown in 1.1. So the first is that E is equal to R minus Y, okay, it's through the summing junction here. Does everybody see that? The next one is that U is equal to C times E. So in the Laplace domain, anything coming into the block diagram, you multiply by the transfer function of the block diagram, so C times E. And similarly with the plant, Y is equal to G times U. So those are the three algebraic relationships. If you say, okay, so how do I know where there's an algebraic relationship in a block diagram? Every block is an algebraic relationship, a multiplicative one, right? So the input times the transfer function equals the output in the Laplace domain. So that's the algebraic relationship that a block is specifying. A summing junction is another spot. So sum up everything going in using the sign that's labeled there. If there's no sign, then usually it's assumed to be plus. But if you have anything that's mixed, you would label each one, hopefully, plus and minus. And then you sum them up and you get the output as what comes out. So R is plus, Y is minus in this algebraic relationship. So that's the algebraic relationship we are, these are the three that this block diagram has. But now in any block diagram you can see that. And along any connective arrow in a block diagram, we have the same quantity. So Y along this whole thing is the same. So U along this whole thing, E along this whole thing. So that's why Y, it's this output here, but nothing changes until it goes through a block or a summing junction. Yeah?
Is our feedback ever represented by a Laplace function? Or is that just kind of assumed to be just the cycling of the system?
So I think what you're getting at is the output always the whole feedback, or is there something in here sometimes?
Yeah.
Yes, there's often something in here, but so if we had a block here in line, this would still be Y, but then this would be like, say, Y2.
Oh.
So this would be some transfer function, say H, and then Y2 would be equal to HY, because you'd be going in to H with Y, and Y2 would be coming out.
Could it just be a converter, though? The input and outputs are different. If it's velocity versus voltage, and you need to convert back to something that's comparable to R.
Right. So sometimes it's just a gain,
Right.
like that. So sometimes this is your actual measurement is in volts, but it's something that you have, say, a constant that relates that quantity, the volts quantity, to a position quantity or to a velocity quantity or whatever it is. So yeah, so it might just be a gain. Excuse me. It might just be a gain. So it could just be, sometimes we'll just represent a gain as like K, which is one way to go. Or sometimes there's a whole transfer function there. A gain is a transfer function, but there might be one that has more complexity to it. Feedback transfer functions. There's a little argument I don't know if I'll be able to get into, but you can always rearrange this so that H can get, the feedback one can get absorbed into the C, you can redefine your controller. So when we do some of these derivations, it'll look like, oh, it's only for this special case of unity feedback. We call it, when we don't have anything in the feedback loop, unity feedback. So this case we call unity feedback. It can be shown that any system can be turned into that. Any system with a feedback controller can be turned into this. So we'll have that argument a little later on. I'll discuss it. But for now, we'll have unity feedback, where the output is our complete feedback to our summing junction. And it turns out that that's not like this super special case that never applies. It actually, you can contrive it to apply all the time. Okay, so closed loop transfer function. So given the block diagram above, so given this block diagram, solve for the closed loop transfer function y over r. So this is the definition of the closed loop transfer function. The output over the command. The transfer function of the plant, obviously, is y over u, but that's no longer our primary consideration. Now what we care about is, when you command something, how does that affect the output? So, how do we do this? It's just algebra, right? I mean, we've got all these algebraic expressions that this block diagram expresses. So let's just go through the algebra and solve for our y over r. So I think it's best to start, I mean, my preference is to start with this y here and say, okay, y is equal to gu, which is just this equation right here, right? So y, and I'm going to suppress the of s because I find it to be kind of cumbersome when I go through the algebra expressions, but just recognize that that's implied. The notation is just being simplified for this. So y equals gu. And let's plug in this expression for u, that it's equal to CE, which up in the block diagram is just saying, oh, u is equal to CE. So G still there. U is now equal to CE. Okay, so we're trying to develop an expression for y over r. We're working our way back here from y. We're getting back now to r is going to come in, right? So now we're getting somewhere. So E is equal to r minus y. So E is equal to r minus y. So G is still there. C is still there. Now we have r minus y. Now, we have a y on each side of the equation. So we're going to want to group those. We got rid of our E, we got rid of our U, which were two things we don't want left. They're variables, right? So U and E are both variables. We don't want them in the final expression. We just want it in terms of transfer functions, right? C, G. So we've got our R, our input, and we've got our output. So our input to this closed loop transfer function is R, right? So we've got all we need, we just need to rearrange. So we'll continue on the next page. Adding the y term, the negative y term to both sides, we have y plus GCY equals GC times R. Okay, so I move that term over here to the left side, factor out the y, and divide both sides by 1 plus GC, which is left over. So y equals GC over 1 plus GC, all of that times R. Now, if I want to find the transfer function I need to find y over r, right? So divide both sides by r, it's just equal to gc over 1 plus gc. And this is our closed loop transfer function. This is the transfer function from a command r to an output y. And when you have a control system, the closed loop transfer function is the transfer function that governs the control system behavior. Okay? Yeah.
Is there a reason? I mean, when I see this, is there a reason why it looks very similar to one of the standard forms of the transfer functions from earlier in chapter 6 or lecture 6? From systems.
It's.
Or is that just kind of a coincidence?
I think it's a coincidence. I mean, like, it's not a coincidence in that the transfer function is always the output over the input. This expression here is, I don't know of any deep reason why it looks like that, but like compared to the standard form. Remember that g and c are themselves transfer functions with, polynomials in s. So when you expand them and simplify, this will be one fraction of a polynomial in s in the numerator and a polynomial in s in the denominator. So there will be poles and zeros in this one too, right? So there will be values of s for which the numerator is 0, so those are the zeros, and values of s for which the denominator is 0, and those are the poles, right? And then we're going to talk extensively about closed loop poles, closed loop zeros, and how, remember, the closed loop poles govern a lot about how the system behaves, right? Stability, transient response. We'll find out also steady state response. So
We're getting there.
we're getting there. We're going to have to talk about how these closed loop poles arise. And then what we care about really at the end of the day is how do we make them go where we want, right? So remember, the plant is whatever it is. Maybe we can change the plant somewhat, but typically G is G, and we can't do anything about it. It's nothing. No, I'm not going to do it. Okay. So C is the controller. We can totally do whatever we want to the controller. So notice how C comes in. It'll come into the poles and the zeros. How we change C is going to affect this closed loop performance. And that's how we're going to talk about, like, we're going to say, okay, how do we choose C so that some of these response characteristics end up the way we want? And mostly we'll do that by talking about where do we put those poles, those closed loop poles. How do we affect whether they are based on what C is? So lots to discuss in terms of that. But yeah, so this is like sort of the foundation, and then we're going to build off of this going forward. Any questions other than that about this stuff? I can go over the exam solution for a minute if you guys want.